This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
In the ground.
Okay.
So these are just for suppressing. This could be 100 nanofarad, you can put 200 nanofarad. So these are the couple of just some standard values we put in. But this will not do the job of this one.
Okay.
You know what I mean?
But this one is like 10 micro F, right?
Yeah. So here
it's bigger than this.
Yeah. So then here what it says is no. I got your question. See.
Yeah.
So this is the USB supply.
Yeah.
From the USB you are getting the current.
Yeah.
And then if some noise is here, that will be going to the ground.
Yes.
Okay.
And then this inductor will prevent the further noise coming here.
Yeah.
And then these are regulator input. So the regulator input, so the regulator, this is not the input source. So this will charge, this 10 microfarad will charge and form a, if this is 3.3, then all the circuit here will be completed here.
Okay.
Because of this 10 microvolt. Then why do you need 10? You can't connect 100 nanofarad because then you can't store that much charge. So that's the reason we need a big value.
Okay.
Then this will be so. Then for this one, if you don't have this one, what will happen is your circuit will be finished all the way in the input part like this. So now what is happening is your circuit is completed here, your input part. Because this USB will be charging to this one, and then when something is happening, then your circuit is closed here, see?
Okay.
For the AC signals.
Yeah.
And then you are getting plus or minus 5 and same thing here. See?
Okay. So the reason we don't use 100 nano F here is because we cannot charge 3.3 though.
No, it will not, you will not get 3.3.
Okay. But why here? So it's plus or minus 5.
No, you can connect 3. No, your answer to your question is so you are connecting first you are going to connect 10 nanofarad.
Yeah.
Then you got the big so many ICs 1, IC2, IC3.
Yeah.
Then when you have 10 nanofarad, this one got your frequency is 2 pi f. Your impedance equal to 1 by 2 pi fc.
Yeah.
Then this capacitance is very small. Then what will happen is when this is small, then your impedance is more when the frequency increases. But if you can put a very big capacitor, then what is happening? Your impedance is already small. You know what I mean?
Okay.
And then plus this capacitor, your capacitance equal to Q into V.
Yes.
Sorry, Q equal to C into V.
Yeah.
The how much charge it can store depending upon the capacitor.
Okay.
And then here, if your power supply is like a drop like this is coming, suppose, then this capacitor will be discharging and making it correct.
Yeah.
If this is not a big value, it won't be able to pump that much, so you will get like smaller.
Okay.
But if you got a big one, then it will be taken care of and it will make it full.
Okay.
So you got many advantages.
Okay.
So this topology wouldn't these two position capacitor change, like instead of
No, not good. Why? Because you got the inductor. You are stopping the noise here.
Yeah.
And then for inductor is short for DC.
Yeah.
So from here you are getting some noise.
Oh, sure.
Okay. Then you don't want that noise is completed like this. You don't want noise coming here now.
Yeah.
So that's the reason we are trying to close it here.
Okay.
So you wanna the decoupling capacitor here is used to shorten noise to ground.
Yeah, ground. Yeah.
And then the
From
DC
here you don't
goes
want. Yeah, DC goes through this one. Yeah, then your input is finished here. So this finished means not for DC, it's for AC. Then there is a switching. It's a switching regulator, isn't it? What is this? It's a regulator.
Yeah.
In the regulator, if the regulator inside got some switching. That's the reason you will be studying switching supplies.
Okay.
That's the reason they can regulate that voltage.
Okay. So here they use the 10 nanofarad. Oh, okay, same. Okay, so these are the same. Okay, okay.
Very well, sir.
Thank you.
Yeah, good afternoon. So this one we already discussed in the last lecture. about distribution strategies. When you have analog and digital part, or you have sensitive part, then what we will do is we will be having a regulator. After the regulator we got a very high capacitor, and then what we will do is we will use ferrite beads, and then we will be putting here one IC, then we have got bypass, and then here another part again bypass, but then these things are isolated. So which we already discussed in the previous lecture about how to connect the decoupling capacitor. And then when you have a ground, as I said, a good rule is to use separate power supply feed lines and return, so that load currents for each sub-circuit to flow in different conductors. Means this is a poor way of connecting the ground, because this ground is connected to this ground is connected here, this ground is connected here. So when you do that one, what will happen, we already discussed see this type of effect. All the current will be adding up, and then because of the impedance of the copper in the ground plane, you may get some voltage drop here, means you may get a ground lifting. In order to avoid that one, it is not a good idea to connect like this. So maybe to have separate grounds, kind of like this, if possible in your design. So this is not a good idea. So then this can be avoided. Maybe you can keep your IC in a different location based on how sensitive they are. So then whenever you are not shorting, because this is a power supply, from the power supply, if you are giving separate power, separately if you give power to this IC, this IC, this IC, then that is called a star topology. So that's what we discussed here. So this one is a bad topology, but then this one is called a star topology. See, your power supply is going separately, and then so that the return is coming here. It is not overlapping with this return. So we will be using the star topology, and sometimes it is not practical to apply star topology to every power supply circuit, because you have got maybe 10 ICs, then you can't have 10 lines for the power supply. It is not practical. In that case, what you can do is there may be too many power supply lines. The key is to understand each circuit susceptibility and partition sensibly. Like it is not possible always to give power supply separately for each IC. Then what you can do is the sensitive ICs, you put it in one side. Then other ICs you can combine together. Especially sensitive ICs and ICs with high current. So this one got a very high current. Then you don't want to messing up this with these ICs return. So you can put this one separately. High current one, sensitive one, maybe you can put it here. Other ones you can combine together. A note on signal grounding. Input and output signals are often more susceptible to grounding issues such as induced noise than power supply lines. The key is to understand where your circuit is referencing the ground voltage relative to your input or output of the amplifier signals. Ground reference voltages must be free of current noise and ideally fixed relative to the input amplification supply voltages and differential input signaling. So these are kind of a summary of what we discussed. And then signal grounding examples. So this is good. Why? Because here is your signal, and then that is coming to the op amp, and then this is a return is going here, and then this is a return to the ground plane. Then this is poor. Why it is poor? Why? Because this is your op amp return, and then here in the return path, then you are putting so many ICs here. See, here one return, here one return, here one return. So that is not a good design. So this is even worse. Why? Because what you are doing is here, at least what you are doing is here you got one IC, here you got one IC, here you got one IC, and all the returns are coming to the return of your sensitive amplifier. That is not good. And then don't connect like that. Then this is even worse. Why? Because your power supply is here, and then you got a separate wire going here, and then your current is going. So this is the power supply, or sorry, this is a signal. From the signal, what is happening is signal is connecting to this amplifier, and then it is going, and then it is coming to the ground, and then this is your ground. So you got two grounds. So you should never connect two grounds like this. So you should have only one ground. See here, what is the problem is here you are connecting one ground to the power supply, and then this ground you are connecting again to here. So better, this is a good way. So then here what is happening is here this can be going to a power supply or a regulator ground, and then you can get the power. But then this one means then you are getting two ground loops. So
to summarize, maybe these slides you might be thinking what I am talking about. So I am talking about star topology. So what is a star topology? So what it says is, so when you have, see, you got a regulator. So from the regulator you got a +5 and then a symbol case 0. Then your IC1, and then if the IC1 need 1, maybe 500 milliamps, then IC2 need only 0.02 milliamps. Then if this is the case, then if you are connecting like this, 5 volt you have connected here, 5 volt you are connected here, and then if you short both the grounds and then you connect to the ground plane. So this is your ground plane. Then what will happen is your 500 milliamps and then 0.02 milliamps, then both are adding up, and then here you are getting some voltage X volt because of 0.2 ohms of your copper. And then here it may be some X volt, maybe X volt may be okay with this one, but then maybe this is your sensitive IC. You know what I meant? Then here if your ground is having X volt offset, then this will affect your IC's performance. Then in that case, then you will go for a star topology. So star topology is, this is your regulator, then this one you will connect to the IC1, and then this is a 5 volt, and then this is the return, this is a return to the ground plane here. This is the ground plane, so this is maybe close to here. Then another one you will be connecting another 5 volt. Then here see the 5 volt we are not sharing, so this is a separate 5 volt. Then this is a IC2, and then this is +5 volt. So that here the current is coming, so this is IC1, and then that is 500 milliamps, and then the return current is coming like here, so in the ground plane. Here you are getting only 0.02 milliamps is coming, and then the return is coming again to the ground here. Here maybe we will be connecting closest point to the power supply, your via will be connecting somewhere here, closest point. Then this one is not much affected. You know what I meant? And then when you have n number of ICs, this star topology will not work. Why? Because you are taking from the regulator each line. See, this one is connecting here, this one separately. When you have n number of ICs, you will be connecting from here another one, here another one. So that is not good. You know what I meant? That is not practical. Then what you will do? In that case, if you got like 10 ICs, this star topology is very difficult. Then what will you do? In the 10 ICs, then in your design you will find out which one is high current one. Okay, then what I will do is, okay, high current one, this again, then what you will do is, you got the regulator, I will categorize the number one IC1 is high current, so I will put it separately, give the power supply +5 volt, and then this is the return coming here, and then this is the 500 milliamps, so that is high current. Then maybe another 8 ICs, all low current, no issues. So then all the 8 ICs I will connect like this. So these are the IC1 to IC8, and then here it is fine, the ground you can connect, because these are anyways the low current ones. Then maybe another one is very sensitive, another 1 IC out of 10, 1 IC is sensitive, so that also you can put it separately. So IC10, so this is IC1, so this is IC2 to IC9, and then this IC10, then you can have a separate one. You know what I meant? So this is called a star topology, so that you are not shorting all together, but you are separating them, and then this type connection separately called star topology. So that's what we have been discussing. Then another thing what we are discussing is, now in the signal grounding example, what I have shown is, so this is a regulator, and then for the regulator, this is your PCB board. So for example, this is your PCB. In the regulator, this is the input of regulator. When you want to use this PCB, what will you be doing connecting? You got an external power supply for a battery, because external. Because otherwise, how will you give power to the regulator? When you are connecting an external power supply, you will be connecting here, maybe this power supply is 5, maybe here you are connecting 5 volt. This regulator will convert 5 to 10 volt into 5, and then this is the ground. So this is the way you should be connecting. You should never connect this ground with this ground, because then you are creating a lot of loop. So that's what we discussed here. So you should have only minimum number of ground connections. The classification of power subsystems. Define subsections for power isolation using an understanding of currents. See, high current motor drive, low current microcontroller subsystems, you have to separate it. Analog or digital circuitry. And frequencies of operation, you should be separating high frequency and low frequency. And then plus or minus analog and 3.3 volt PLL sections, phase locked loop, we will study later. So now first we studied analog and digital, but then you also have to take into account high current and low current. Otherwise that also will create a problem. But in your case, in the DSO, you don't have a low current, high current scenario. So you got mainly digital and analog. Then you got USB as well. And then frequencies of operation. When you have high frequencies, put it one price. Low frequencies, you put it some other area, so that the high frequency, the signal path should be as minimum as possible. Use appropriate decoupling and topological separation to isolate noise with each subsection and prevent leakage into interconnected subsystems. So once you know how the noise is generated, once you know how the return current is going, when you design your PCB, now you will be thinking. Previously, when you design without knowing these things, when you design your PCB, you are just following some rules, that's all. Put my components here, I don't like here, put it on the right. Then evening you thought we'll put it down, then in the afternoon you thought next day I will put it up. See, because you are just following some rules. When you know these things, then that will bring a new dimension to your PCB design. Now you know that you are knowing and you are applying the knowledge in the PCB design Altium. So that is the difference between a technician designing PCB and an engineer designing PCB. So for example, in big organizations like in my previous space organization, we don't design the Altium. Means obviously we design, but then we got technicians. So then they will sit with us and then we give the footprint. You create the footprint and then they create the footprint. But then they will not do any placement. So we have to tell them, you put this on here, this line should be coming here, because they don't take any these type things. They know how to use Altium, that's all. They can make very compact board, how many layers, all these things they can do, but some engineer should sit down and then tell how to put the components, where to put it. So that's the reason. So these things a technician might not know, but engineer knows. So that's the difference between a technician using Altium and an engineer using Altium. So then another section is PCB fabrication and PCB tracks. So that is relevant after you submitting your PCB. So now we will go back to another section, that is analog to digital converter, and then which we already studied. I will be talking about DAC, because in your DSO you got DAC. So when we talked about analog to digital converter, we know that we got so many comparators, and then comparator got a different threshold, and then when you have an analog signal coming here, and then depending upon the threshold here, so this comparator, you got 7 comparators, and then you got 10 volt you applied to the input of all the comparators. Then this comparator we connected 1K, so that here you get a comparator threshold is 1 volt. For the second comparator threshold is 2 volt, 3 volt, 5 volt, 4 volt, 5 volt, 6 volt, 7 volt, and so on. So that is the reason when your signal here it is 10 volt, but here if it is 0 volt, what will happen? All the comparators, nowhere it is crossing, so you get 0, 0, 0, 0. Even if you connect here 0.5 volt, what will happen? None of the comparator will give a high, because your voltage is much below the threshold, because this is the comparator which has got the lowest threshold, that is 1 volt here. And then it is not, this is analog input. So this 10 volt is we already connected here, that is your DC, and then why we connected this 10 volt here? So this is your analog input. So your analog input is going to the inverting terminal of the comparator, and then from the non-inverting terminal we have connected resistances. Then we connected a 10 volt constant voltage here, 10 volt here. Why we have connected 10 volt? So this 10 volt is for getting different threshold voltages. And then so when this is 10 volt, so what is the voltage here? Yeah, so this is 2 volt, 3 volt, 4 volt, 5 volt, 6 volt, 7 volt. So then we will be connecting analog signal here. So when you connect analog signal here, when your analog signal is 0.5 volt, what will happen is none of this comparator will trigger the output, because here it is 1 volt. If it is more than 1 volt, you get maybe this comparator will give an output, still this will not give. So that is the reason when your input voltage, this voltage is less than 1 volt, then all the comparators will give 0, 0, 0, 0. When it is above 1 volt, then what will happen is this comparator will be giving an output high, but then here the threshold is 2 volt. So that's the reason 1 to 2 volt only A will be giving high. When the voltage is above 2 to 3, then you are getting A and B high, A and B of the comparator high, remaining 0. When it is more than 7 volt, all the comparators will be giving an output. You get 1, 1, 1. See, so that's the reason. Then we use a encoding logic, and then we get 0, 0, 0. Because when you put an encoder here, see, this is an encoder example. This is a 1, 2, 3, 4, 5, 6, 7, 7 to 3 encoding. And so then you are getting, see, less than 1 volt you are getting 0, 0, 0, and between 1 and 2 you are getting 0, 0, 1. So here what you are doing is you are converting your analog into digital, which we already discussed. Now the question is, somebody came up with this idea, then somebody wants to do the other way around. So you will have digital signal, but then you generate analog signal. So that is a DAC, digital to analog conversion. So how will you do DAC? So how people came up with the idea of DAC? For that we should study inverting amplifier. So we already studied inverting amplifier using operation amplifier. So let us take infinity gain, means open loop gain is infinity. Then when you have inverting amplifier, your non-inverting terminal will be grounded, and then you will be connecting signal to the inverting terminal, and then this is the inverting terminal topology. And then we know op amp V out equal to A0 into V in 1 minus V in 2. So V in 1 means V positive minus V negative. And then because of the virtual short, when this is grounded, because of the negative feedback, this also will be virtual ground, 0 volt, because of this reason, because your gain equal to open loop gain equal to infinity, so that V in 1 minus V in 2 equal to V out by A0, and then A0 is equal to infinity, so your V in 1 equal to V in 2. So when the op amp is having negative feedback, so please, somebody asked me about positive feedback, this is happening only the negative feedback. So the virtual short, the idea of virtual short happens when you have negative feedback, or negative feedback is predominating in your circuit. Means op amp will make sure that inverting and non-inverting voltages are same. And then because this is grounded, this also is virtual ground, because of the virtual short concept. These are virtually shorted. So that is good for analyzing the circuit. So then what will happen is this is 0 volt, and then when this got an infinity gain, the current going into the operation amplifier is almost 0. Current going into the operation amplifier input. So that is the reason from your signal the current is going through the R2 and then come to this point, and then it is going through RF and coming out. Actually the current is not going into the input of the operation amplifier. So then we can write down the equation 0. So I am going to write down this K, I am going to write down the KCL. So this is, what is the voltage? 0 voltage. 0 minus V out divided by R1. So that is the current flowing this way, and that current should come from your V in, because your V in current is coming, passing through R2, coming to this point. There is no current is going into the input of the operation amplifier. For ideal operation amplifier, 0 current going in. For a real one, it could be in pico amps. So still it is negligible. So that is the reason the current from V in it is coming, passing through R2, coming to the point X, and then coming out like this. So that is the reason 0 minus V out by R1, this current is provided by this R2 from this V in. So V in by R2. So V out by V in, which is equal to minus R1 by R2. So that is a gain of your inverting amplifier. And infinite A0 forces negative input to be virtual ground, which we already discussed in the previous lectures, and so that's the reason minus R1 by R2 is coming. So inverting amplifier, then somebody made some modification of inverting amplifier. What they did is they connected two resistances, R1, R2. In the previous case, you got only R2, one resistance, and then one resistance you connected here. Somebody now connected from, because anyway this is 0, and then they connected another resistance, something like this. So when you connect two resistances, and then we just changed the labeling. So we RF, this is a feedback resistor, so we put RF. Then your V out will become how? Previously it was R1, this is R1 or RF by R2. Now you have got 2, and then so your V out equal to V in into minus R1 by R2. When you have two resistances, then your V out equal to minus RF, because that is common, into V1 by R1 plus V2 by R2, because then you are not only you are using two resistances, here you are using two different voltages as well. See, you are connecting maybe one voltage V1 here, another voltage V2 here, then you are using two different resistances. Then we can write V out equal to minus RF V1 by R1 plus V2 by R2. Suppose you use same resistances, then you can write V out equal to minus RF by R1 into V1 plus V2. See, it is an adding the voltages. So this is called an adder. Your voltage is being added. So this is called adder. So then that is the idea behind the digital to analog conversion, DAC, a symbol. And then this slide I really like it because this one carries all the information in one slide. A DAC can be used to convert the digital representation of an audio signal to an analog voltage that is then used to drive speakers. Means you need DAC even in your audio signal. Like if I got my microphone, in the microphone what is happening? I am talking, then the microphone, inside the microphone you got a diaphragm that is vibrating, and then that is analog signal. Then you got analog amplifier, and then that amplifier is amplifying the signal. Maybe you got a filter of my sound filtering. Then what you will do? Then you need to do processing. So it will convert into my analog signal. My sound will be converting into digital, and then doing all the processing. Then you are getting the processed digital signal. Then the processed digital signal, can I connect to the speaker? How many of you think that we can connect a digital signal to speaker? You cannot connect your digital signal to speaker, then what sound you will hear? So you need to convert the digital to analog, then you connect to that speaker, because what speaker is doing is exactly opposite of what is happening in the microphone. Because when I am talking, the diaphragm is vibrating analog, and then that is analog signal. So what you are doing is the reverse of this microphone. You are giving the analog signal to the microphone, analog signal to the speaker, and inside the coil is vibrating, and then your diaphragm is vibrating, you are getting the sound. So in the real world it is analog. When you want to give something again back to the real world, it should be analog. And then so that is the reason then here you need to convert your digital signal to analog, and then maybe amplify the signal again and then connect to your speaker. So that's the reason we need a DAC. So this is an example. It said audio signal you have to convert back into analog, then only you can connect to your speaker, then only it can drive it. Then how can you make a DAC? The DAC you can make again using a voltage adder. So this is a simple 4-bit adder, or 4-bit. It is called a 4-bit DAC. Why? Because you got only 4 inputs. So the concept is very simple. You are making a digital to analog conversion. How you are making? Here again you are connecting some, say, 8 volt DC, and then 8 volt DC we connected here. This is a switch. S1 is a switch, S2 is a switch, S3 is a switch, S4 is a switch. And then here we have connected 10K, 20K, 40K, 80K. So these values can be different depending upon your application. Then in the feedback we have connected 5K. Then binary numbers. So all the switches, so this binary, these switches we can implement using transistors. So whenever you want to implement a switch, you can use a transistor. And then my question is, when all the switches are open, or when all the switches are connected to 0 volt, what you will see here? Yeah, so that is 0. But then when S1 is connected close to here, and your 8 volt is here, so that's your digital high. So digital high is 8 volt. Here you have connected. So if S1 is connected here, then what is the digital value? So 1000, and then 5K divided by 80K. So that's the reason you are getting 0.5 volt. And then when S1 and S2 both are on, then what will happen is you are getting 1100. So that is your input. then you are getting an analog voltage of equivalent of 1.5 volt and so on. When all are ones, and then this you are getting around 7.5 volt. See, so you are getting digital input. So these are your digital input. In the transistor, you are connecting your digital input, and then so here my question is here the 8 volt we have connected, that is a DC, and then here how will you make the transistor? Here when you have a switch, then you might be connecting your digital signal to the gate or base. You know what I meant? So here if I draw it, no, because I think some of you got confused. So how will you convert this one? So then, so what I am going to do is, because this is very important to understand the concept, then only you will be able to make new designs later. So we know the concept of adder. So adder means, so this is your feedback resistance RF, and then so that is we have put here 5K. Then what we got is from here we got 800, and then from here another resistor, then here another resistor, from here another resistor, all are coming, and then this is 10K, and then this is 20K, 40K, 80K, depending upon what voltage you wanted at the output, and then this is grounded. And then here what I will do is I will be connecting a transistor, a simple transistor, common emitter, and then this is my one line. Then here, then this I connected to some voltage, see. Then here also I will be connecting another transistor, and then this one is another line. Then here also I will be connecting a transistor, and then this is connected here. Here also I will be connecting a transistor. Just an example. And then this is some DC voltage. So that's the reason maybe I said here 8 volt or something you have connected. And then from here again I am taking one out. So here I am taking one out. And then so this is S1, S2, S3, S4. So these are my inputs. So when I take it out, and then so S1, S2, S3, S4. So that is my input. You know what I meant? And then you got a 4-bit digital signal. So I'll connect here S1 1 0 0 0. So that is my first string. Then what will happen is this transistor will be on. Then this 8 volt will come through this one. This is on. This switch is on. And then 800. So how much voltage you will get? 5 or 0.5 volt. So that is the reason I am getting 0.5 volt. See, this is an analog voltage, and then I am giving a digital signal 1 0 0 0. I may get 1 1 0 0. How much I will get? 1.5. Yeah, same like 1 1 1 1. Then what I will get is 7.5 volt. See, so then that's the reason when you have a digital signal, now you can convert to analog. See, it's a simple concept using voltage adder. And then when you have this DAC, then the people might be asking a question, what is a LSB? LSB means the least significant bit. MSB means most significant bit. So LSB, that is here, this part. Because here if it is changing, the change is very small, 0.5. See, least significant bit means that is a kind of resolution or the step you can get. So your analog signal will vary from 0.5 to 1.5. The step size is 1 LSB, that is 0.5 volt. So that's the reason we are using the inverting amplifier. So that is a idea came from the inverting amplifier. And then we studied the voltage adder, then we studied now the digital to analog converter. Now we are going to study some characteristics. And by the way, where we will be using DAC in your design? So you said not using. So where you will be using DAC in your DSO design? Yeah, trigger, that's good. Yeah, in the trigger circuit, definitely you need a DAC in your design. And as I said, some of you asked me a question, if your signal is inverted before the ADC, what you will do? You don't need another amplifier to invert it. You can connect to the inverting input of the ADC. You know what I meant? So what I meant is, because so many people asked this question, I thought I will discuss in the class. So this is a question. So this is your BNC connector, and then you got so many stages, and then this is your ADC. Then the question is, your signal is something like this. Just before the ADC, this point, your signal got inverted. So what will you do? Because ADC got inverting and non-inverting, so then you can connect your signal to the inverting terminal. You know what I meant? And then when you design your trigger, you take the comparator and then you give this to the negative. So that's all. You don't need to put another op amp and inverting it. But if your signal is positive here, if your signal is again positive here, you don't need to connect to negative, you can connect your positive. Maybe I'll draw it properly. So case 1, no inversion. Then what will you do? So BNC, the signal is like this, signal, and then you got so many blocks, ADC, and then you can connect to your positive, so no inversion. So your signal here is inverted, so you can connect to the non-inverting, and then for the trigger you can connect to the positive, so that's fine. But then case 2, so case 2 inversion. So if you got inversion means your BNC, and then your signal is like this, so many blocks, ADC, so when you measure it your signal is inverted. Then this you can connect to the inverting terminal, and then from your ADC trigger circuit you can connect to the negative one, so that that issue can be solved. Then ideal transfer characteristics. Then one LSB. So that is how will you find out what is one LSB value for a ADC? So 1 LSB equal to full scale range divided by 2 raised to n minus 1 for n bit converter. So full scale range, you can see when we are designing a ADC or DAC, then you can see here this is an ADC. So when you are designing an ADC, we got some voltage range which is decided by this voltage. So that's a full scale range that will decide the LSB. What is a LSB? So that is the reason here you will see 1 LSB for the ADC. How will you find out 1 LSB? Because 1 LSB is the smallest step you can get. So that is equal to full scale range FSR. It is called full scale range divided by 2 raised to n minus 1. N is the number of bits of the ADC. For example, if full scale range is equal to 10 volt, so how will you find out the full scale range? ADC will give you the full scale range, you can find out, or your design you can take full scale range, how much you want to do. Full scale range equal to 10 volt, then 1 LSB equal to 10 volt divided by 255, because if it is 8 bit ADC means you got 8 output lines. If it is 8 output lines, it is 2 raised to 8 minus 1, that is 255. So 39 millivolt. So what do you mean by 39 millivolt? 1 LSB, one least significant bit is 39 millivolt. Means that is a step size you will be getting. Means your ADC will not give you any output unless your input voltage is more than 39 millivolt. So that is the minimum resolution you can get. Then if your application is sufficient, like you want to measure only the increment of 39 millivolt, then you can use 8 bit for a given FSR of 10 volt. But if you want a very high resolution, you can see you can use 8 bit, 9 bit, 10 bit, 11 bit, 12 bit, 16 bit. So if you use 16 bit, number of increments 2 raised to n is big number. Then if you are using in the 0 to 10 volt range, because if your signal is varying from 0 to 10 volt, that is your input signal range, then what is the minimum voltage? 152 microvolt. So that is a step size. If you are using 10 volt range, means 0 to minus 10 to plus 10, that is your input range, then your resolution will be 3.5 millivolt, means double this one. See, then half LSB, which is equal to half of this one. See, that is the reason if you are using 16 bit, then your step size is 152 microvolt. So you can measure 152 microvolt increment. But if you are using 8 bit, then you can get maybe 39 millivolt. So that is in millivolt only you get it. So that is the reason when you plot your binary output versus analog input, then you will always have some step function for the ADC. So from this we will go to the document camera. So what it says is I want to design an ADC, and then this is my ADC. So this is the input analog. Then you are getting the digital, so many digital lines. Then I am going to plot it. So this is the digital output versus analog input. Okay. So what will be my ideal situation? I want something like this. So this is maybe, this is 0, 0, 0, maybe this is 0, 0, 0, 1, 0, 0, 1, 1 and so on, and then this is maybe 0.5 volt, 1 volt and so on. So I want this straight line. Is it possible? Then what is the resolution of ADC? If I want a straight line, yeah, but then the resolution, I am talking about the resolution. Step size is 0, then the resolution might be infinite number of bits. And then, but ideally, if you are using 8 bit, and then if it is 10 voltage range, 0 to 10 volt, you are going to use it. In the input, you are going to give 0 to 10 volt. Then what will happen is, so this is 0.05. So up to 0.5 volt, you get nothing. Then what will happen is it will go up, and then you will be like step function. So your increment is always like a step, not a straight line. And then this is equal to how much? 1 LSB, that is equal to 0.5 volt. So if you increase the resolution, you can reduce the step size, and you can't get a straight line, then you need infinite number of bits. So that's what it shows in the slide. See, from here nothing will happen because that is your LSB, and then it will jump again, it will increase, nothing will happen. When it is 0.001, and then when the voltage is exceeding, then it will go to here. Then again it will get a step resolution. So that is called 1 LSB. So means when 1 LSB, if you want to get, you need to have some range. Then another question, if you are using flash ADC, it is called flash ADC. Flash ADC is ADC because ADC architecture itself is a big subject in some universities. So flash ADC means FLA as such. Flash ADC means ADC use comparator, because ADC can be made in different ways. The simple one what we have studied is called flash ADC, where we are using a comparator for making the ADC. Then so we can find out here, if you go back to the ADC, for a 3-bit output, 3-bit, 1 to 3-bit output, how many comparators are required? 7. Then you can find out how many comparators are required. See, 2n comparators for 8-bit ADC. If you want to make an 8-bit ADC, you need 255 comparators. So that is the complexity. Then think about, you are making 16-bit ADC. Then you will be having so many comparators. Each comparator got how many transistors? So many transistors. Even LM741, you know that you got around how much? 26 or 27 transistors. So into 26. So that is a design complexity. So you take your 8-bit ADC, take it granted, put it there, throw it, but you can understand how much complicated it is. And so 1 LSB, we already discussed it. 1 LSB, if it is a 3-bit and then ADC, then your 1 LSB equal to 1.42 volt. So that is not very useful if you got a step size of 1.42. Then again there is always a quantization error. People will be talking when the ADC, they will say quantization error. What do you mean by quantization error? So your quantization error means if your ADC is 8-bit and your voltage range is 10 volt, 0 to 10 volt is your input, then what is 1 LSB? That is equal to 0.5. So if there is any variation within that, you don't get it. So that is called quantization error. So that's the reason we plotted this one, plus LSB minus LSB. So your accuracy will be 1 LSB. So then you will have this much error in the sampling. The error in the sampling means you will be connecting 0.5 volt or 0.49 volt. You won't get any output. When it is 0.5, you get 0, 0, 1. If your 1 LSB equal to 0.5 volt, when you connect the input to 0.5 volt, you get 0, 0, 1. Then your input increased from 0.5 to 0.7. Your output is, you are not going to get anything. So you have to wait until it become 1 volt. Then your ADC output will change 0, 1, 1, something like that. So that is called quantization error. Then another one is another characteristic you will see is resolution. Yeah, it's very important. Resolution versus accuracy. Many times people get confused for ADC, resolution versus accuracy. So resolution does not imply accuracy, nor does accuracy imply resolution. But then what is resolution? Resolution and accuracy are not identical. And we are talking in terms of ADC. An ADC may have 16 bits of resolution. So when you talk about resolution, you can just count how many outputs are there per digital output. 16 bit, that is a resolution. But ADC or the circuit accuracy may be much less than the resolution because of the internal or external error sources. So what it says is when you take 16-bit ADC, then when you go back 16-bit ADC, you will see that, oh, my resolution is 152. This is not accuracy. This is based on the design, we calculated this as 0.152. But in practically, when you do the measurement, you always get less than 152 because that is theoretically calculated based on your design. So that is a resolution. Accuracy is when you connect in the circuit, how much you get it. Maybe then you get only 200 millivolt. Then that is accuracy. Not 152, much higher than. So then why that is different? Why? Because there are so many errors when you design the ADC. Gain error or scale error, offset error, DNL, it is called differential nonlinearity error, missing code. So these are the errors when you make an ADC, you will encounter these type of errors. Then external reference or supply noise, your supply might have some noise and then you may have some clock jittering problem. We'll study clock jitter. So these are due to external reasons. So when you design ADC, you will never get your resolution. If it is 18-bit, 16-bit ADC you are designing, you don't get that much calculate resolution. It will be much less because of these errors. So what are these errors? So then that is, for that, whenever somebody is designing an ADC, they will find out the signal to quantization noise ratio. They will find out. Again, you don't have to derive the expression. So some people say it is a SQNR. So SNR, they will calculate for sinusoidal. They also may calculate for triangular waveform, input waveform. So for sinusoidal input, they have already calculated, which is equal to 6.02 into n. N is the number of bits plus 1.78 dB. So this is a signal to noise ratio. And then there is another called effective number of bits. So this is the one thing a design engineer should be keeping an eye on. So again, you can calculate effective number of bits from the signal to quantization ratio. So effective number of bits, again, if you are using sinusoidal input, which is equal to SNR total in dB minus 1.78 divided by 6.02. So these numbers, again, the derivation you don't have to use, you don't have to derive it. And then effective number of bits, if you are using triangular waveform, SNR total in dB divided by 6.02. So these are some important concepts, especially effective number of bits. Then effective number of bits will give you the idea of resolution. So my example, when I designed one ADC for the first time, I used a 16-bit ADC. So in my application, actually 16-bit was not required. But then I thought, okay, 16-bit ADC got very high resolution. You can see 16-bit is around 152 microvolt. So that is the 16-bit design. Then I claimed, I will be getting 152 microvolt in my document. Like, this is the resolution. When I made the board, when I started testing, the first thing what I found out is I got something like this, because this will happen. So that is, then you will understand what is the effective number of bits. So I tested. I made the board. So then this was ADC in my case. then the input was coming, and then I got 16, 1 to 16. Then I thought I will be getting a 16-bit resolution, that is around 152 microvolt, that is my resolution. But actually what happened is, when I made the board around 1 to 10, then what I did is, how I tested my ADC. In your case also, how will you test your ADC? I connected a DC voltage of 1 volt. Then I tested what is the output I am getting. From this digital value we can calculate whether I am getting 1 volt. You know what I meant? Then when I put 1 volt DC, from 1 to 10 was stable, from 10 to 16 was jumping, just but I connected only DC voltage. Then I started thinking why it is happening. Then I thought my DC got something, AC going in, but then I found out this issue came because of my poor ground plane. Because this ADC, I did not put a proper isolation between analog and digital. The isolation was not good. Then I designed my second board, because then this noise is coupling. Because if your noise is above 152 microvolt, then it starts jumping. You know what I meant? And then I designed another board with very good isolation. Then I could make up to around actually 13 bits stable, but still 3 bits are jumping. When that 3 bits are jumping, well, because I was a junior system engineer, and I told my boss, yes, 14 bits that is fine. Then he said, yeah, very good. But then I said, what about 3? Then he said, did you read the data sheet again? Then I went and read. Then in that data sheet they said the ADC is 16 bit, effective number of bits is only 14. And they said 14.5 to 15. Means remaining bits, then what will happen? The line is there, but that will be jumping. You can't take it. So that's the reason effective number of bits is an important thing you have to check. So effective number of bits. So for example, an ADC, you can see, this is example. See, 16 bit. Then you will be excited. Oh, AD9461, 16-bit ADC. But then inside they said you have to read its features. Then you have to look for what is the effective number of bits. Oh, sorry. So what is the effective number of bits? Then you have to read. So then you may say that analog devices and 16-bit ADC 130 mega samples per second, excellent. And then you might think, okay, 16-bit is actual resolution. But then when you check it, there's an effective number of bits. See, that is depending upon your frequency. If you are using 10 megahertz input, your effective number of bits is how much? 12.5. What do you mean by 12.5? Forget about 0.5. Because so 12 bit will be stable. Remaining 13, 14, 15, 16 will be jumping. You can't rely on those. So this is means again, this one is for the best design. If your design is crap, you are not isolating ground planes, you will get 10 bits. Remaining kind of useless. So that is the reason when you find out some other for your application. If you use 225 megahertz, effective number of bits is around, I wouldn't say point fraction, I wouldn't believe 11 bits. Then you have to think whether you need a 16 bit remaining. Why do you need the plane there? Why do you need that line? You can't rely on for the good design. Then maybe better to use an 8 bit if you don't need this much resolution. Then your complexity reduced in the design. So that is called effective number of bits. So in your case, it is not at all 8-bit ADC. Usually, even if you make a mess, it will be 7 point something. So you don't have much issue. This issue happens when you have more number of bits. So that is the reason you have to always look for the effective number of bits. So effective number of bits will take into account all the noises inside the ADC. And maybe I'll stop here and continue in the next lecture.
So it, what I was thinking was if I give 1 volt, the resolution may not necessarily be all 16 bits.
So based on that, they are discussing the concept of the resolution is perfect. Like the ADC
No, ADC, when you say resolution, they are not talking about any jumping bits. Okay, so depending upon your design, you are telling resolution. Okay, so you are using 8 bits, then you got a 255 comparator. And then the flash you are